Yeah. Now let's look at this common types of probability distribution. Yesterday we have simply looked at if it is a continuous distribution or a discrete distribution. Some of the properties we simply said that each individual probability should be between 0 and 1. Sum of all probabilities should be equal to 1. But out of that, if there are some common scenarios, see, why do we typically use these probability distributions? One, to model our business processes, right? How does let's say I want to do some kind of a modeling for number of claims that can occur during a particular period. During 1 year, what is the chance of getting 20 claims? What is the chance of getting 40 claims? I want to model something like that, right? So anything where I want to model something related to the discrete items. What are these discrete items? Countable kind of items. Number of claims, number of successes, right? Number of something. Whenever we are trying to model number of something, we are talking about discrete probability distribution. So various kinds of models that are available for modeling number of something. And any kind of these models, for whatever we are going to discuss now, there are three important things that we need to understand. One, in which context I can use this kind of a model, right? For what business purpose I can use this kind of a model. How do I find out the probabilities using this model? And finally, I am also interested in finding out what are the characteristics of this particular model. Characteristics are nothing but the mean, the variance, something like that, right? For each of the model, how do I identify whether it is a form of uniform distribution or a binomial distribution or a Poisson distribution? What makes me identify that it is belonging to that category of distribution? Once I know that it is a particular type of distribution, how do I identify the probabilities of that particular occurrence of number of occurrence of one event or two events or whatever it is, number of something, and what is the average of it, what is the variance and standard deviation, sorry, mean and variance and the standard deviation associated with them, right? So we'll start off with the uniform distribution, the first of them. Simple. See, formulas wise you need not memorize, because most of these formulas are given in the tables. So the intention of this exercise should not be memorizing of the formulas, but understand where I should use these kind of distribution, for what kind of a purpose I can use this distribution, or from a business example which he has given, how can I convert it into this distribution, right? Those are some of the aspects that we need to understand. So the first of those distributions is the uniform distribution, where all the items have equal chance of occurring. All the outcomes which we are talking of, if they have equal chance of occurring, let's say for throwing a dice, right? We can get 1, 2, 3, 4, 5, 6, and all of them have an equal chance. It's a fair dice. If it is a biased dice, where some edge is broken or something, where there are some high chances of getting some number compared to the other number, then it does not follow a uniform distribution. But if it is a fair dice, or where people say equal chance for everyone, right? Whenever I say that there is an equal chance of occurring, I can simply take the probability of occurrence of each of them is nothing but 1 by 6. How did I get this 1 by 6? Because there are 6 possible outcomes here. There are 6 possible outcomes. So each outcome has a chance of 1 by 6. So whenever I create a distribution of this form, whenever I see any example where the distribution is of this kind of a form, we categorize it as a uniform distribution. Now, in our earlier chapter, what we have simply said is this is a discrete distribution. We did not call it as uniform or whatever. We said this is a discrete distribution. So for every distribution, what did we do in that chapter? We found out what is the mean of that mean. How do I find out the value into the corresponding probabilities and then add up? And variance we have found out expectation of x squared minus expectation of x whole squared. So for this I can find out the variance. Now what they say is, if at all I know this distribution is following some kind of a pattern, the mean and the variance, probably you don't need to sit and calculate doing this entire exercise. They are outrightly known. They are derived. What you are doing is the same. Let's say in this exercise, if I want the mean, 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6, which actually comes out to 21 by 6 or 3.5. What he says is, don't do that entire part. If you know that it is a uniform distribution, take the mean as n plus 1 by 2, where n is your total number of variables. So 6 variables are there, right? 6 outcomes are there. So you directly say that the mean is 3.5. You are not even calculating it. Well, if you calculate also, you will get the same thing, right? The same way variance. Now, if I have to calculate the variance, I have to do expectation of the typical way is variance is expectation of x squared minus expectation of x whole squared. This is the formula which we have looked at earlier, right? Expectation of x we got as 3.5. So expectation of x squared we will get by substituting x squared in place of x for the first row, and then multiplying it with the corresponding probabilities. And after I do that, whatever I am getting is the variance. Now it says if it follows a uniform distribution, you don't need to do that entire aspect. The variance is directly coming out as n squared minus 1 by 12. N is 6 here, 36 minus 135 by 12 is the variance. If I know that the particular distribution is a uniform distribution, then I can very well say that the probability of occurrence of each of them is 1 by n. The mean of it is n plus 1 by 2. And the variance of it is n squared minus 1 by 12. Right? Of course, no point in memorizing, but so you need to understand which scenario I have to use it. If all of them have equal chance of occurring, I can use this uniform distribution. Now, the next one is called as a Bernoulli distribution. See, in the uniform distribution, we talked about n number of outcomes, right? And all of them have equal chance. Now, the Bernoulli distribution says there are only 2 outcomes. Even if there are 6, you create them as 2. Success, failure. What you want, you call as success. Again, success is not an English word called success. Here it is what you want. What you want to observe is called as success. What you don't want is called as a failure. Let's say when I am throwing a dice, right? When I am throwing a dice, if I want 6, so 6 is a success. other than 6 is a failure, which means there are only 2 outcomes for me. Right? Of course, in isolation, we don't look at too much into the Bernoulli. The Bernoulli actually will be used to a large extent in many other distributions. In the binomial distribution, we'll use this mechanism called Bernoulli. In geometric distribution, the next which we are going to discuss, there also we use this Bernoulli. So Bernoulli is just a base for us to understand. We are not talking about outcomes here. We are trying to group the outcomes into only 2 outcomes called success and failure. Right? Only 2. And so the probability of success is P, then the probability of failure will be 1 by P, 1 minus P. Right? And so the simple way, if you want the probability of success or a failure, you can simply take it as probability. Let's say if I want probability of x equal to 1, which means it's a success. I want the probability of success. I can write it as P of P power 1 into 1 minus P to the power 0, which means the probability of success is P. And when I say probability of failure x equal to 0, you put P power 0 into 1 minus P to the power 1, which is nothing but 1 minus P. So, simple way to understand Bernoulli, it is not a big thing to understand. All I need to find out is probability of success and probability of failure. Now, simple logic is, if at all if I am throwing a dice and I am planning to observe a number greater than 4. Number greater than 4 is a success. So, 5 and 6 are becoming successes. 1, 2, 3, 4 are becoming failures. So, the probability of success P is 2 by 6, 5 and 6. So, 2 by 6 are 1 by 3 and 1 minus P is 2 by 3. So, just calculation up to this stage is the intention of Bernoulli. Now, these 2 values will go into my binomial distribution as some of my inputs in the next slide. Right? Now, the most important or one of the most important distributions we need to be aware of is a binomial distribution. Few things. The same Bernoulli distribution, right, where there are only 2 outcomes, success and failure. Now, if that same experiment is repeated n number of times, let's say throwing a dice. When I am throwing a dice, there is some probability of success. Success is whatever we define. There is some probability of success. There is some probability of failure. Right? Whenever I throw a dice. Now, if that same dice is thrown some n times, right? If that same activity is performed n times, there may be some number of successes out of that. Let's say I have thrown the dice 20 times, right? There may be at least 5 times I would have got a success. 15 times I would have failed. Success, if I say, getting a 6 on the dice. So, anything other than 6 is a failure. So, that's the first step. It should be a Bernoulli. What is the definition of a Bernoulli? There are only 2 outcomes in that, success and a failure. So, here I am creating success means getting a 6 on a dice. Failure is not getting a 6, anything else. So, it is a Bernoulli. I am repeating the experiment 20 times. I want to observe what is the chance of getting 5 successes. But here 2 important points that we need to understand are, all the trials need to be independent. What do I say independent? The outcome of the first does not influence the second. So, when I am throwing the dice second time, it is not influenced by the first one. Right? The result is not influenced by the first one. Then only it becomes, you will apply the binomial. 2, it should be identical. Same experiment. The probability of success and failure should be the same. Right? When I throw a dice, anytime I throw, getting a 6 is 1 by 6 only. So that is what we are calling as identical. These kind of data, probably at slightly later point we'll discuss in more detail. We call that as IID data, called as independent and identically distributed data or distributions. Independent and identical distributions is nothing but each activity, even if you are repeating the experiment n times, no experiment is no task is related to the previous task. The same activity you are repeating n times. The same throwing a dice you are doing it n times. But none of them are related. Right? No dependency. And 2, the chance of success is same across. If that is the kind of scenario, I'll call it under the binomial distribution. So typically, the scenario where I can use this is, I have n experiments being performed. Out of that, if I want, what is the chance of getting x successes? What is the chance of getting x successes out of that? That is where we use the binomial distribution. So typically, the probability is written like this. This part is the Bernoulli part only, if you see. P power x, 1 minus tp. See, out of n times the experiment is performed, I want x successes. So the probability of success to the power of number of successes, probability of failure to the power of number of failures. So out of n times, if I am doing it, if I am getting x successes, obviously I am getting n minus x failures. So the formula for getting x successes, the probability of getting x successes is nothing but NCX, which is a combination form. The probability of getting a success to the power of number of successes, probability of getting a failure to the power of number of failures. This is the probability of getting x successes out of n trials being performed. You will write that as the typical notation is binomial NP, which means the experiment is performed n times, right? And P is the probability of success. Experiment is performed n times, P being the probability of success. The distribution can be written simply as, so in that I will find out what is the chance of 1 success, what is the chance of 2 success, what is the chance of 3 successes, and so on. And if at all I see the distribution is so probably it's like probably in the insurance world, if I have to talk about what is the probability, let's say I have picked up 10 policies, right, at random, right? And if I say the chance of one policy, there is a 10% chance that, a simple example, there is a 10% chance that a claim will come on a policy. Right? Historically, I would have seen, I have issued 1,000 policies last year. There were 100 claims. The practical application I am trying to bring out. There are 1,000 policies that are issued last year and there were 100 claims that were made. Which means the chance of claim present on one single policy is 10%. Right? Now, if I say, if I pick up any 10 policies at random, what is the chance that at least 2 of those policies will have claims? So, getting a claim, I will take it as a success. Probability of a claim or probability of success is getting a claim or having a claim, filing a claim. Probability of failure is not filing a claim. So, in that case, probability of success P may become 0.1, 10%, 1 minus P may become 90%. Now we are saying, okay, I am pulling out 10 policies in this month. Right? I am pulling out 10 policies in this month. What is the chance of getting 2 claims out of these 10 policies? So I will write it as 10C2, 0.1 to the power 2, 0.9 to the power 8. This is what is the chance of getting 2 claims in 10 policies which are being pulled out. Right? So if this probability is high, they'll take some appropriate action and things like that. Now look at this. So look at this numerical. We'll solve this. The same logic. What is the probability that at least 4 out of the 6 questions which have been answered are correct if the chance of answering a question correct is 80%. So probability of answering correct, if I take it as success, it is 0.8. Not answering correct, I'll take it as a failure, which is 0.2. Correct? Now, I am talking about 6 questions being answered. I want at least 4 correct. Right? Which means there could be 4 correct, 5 correct, 6 correct. At least 4. So what is the probability of 4 correct? 6C4 into 0.8 to the power 4 into 0.2 to the power 2. This is 4 questions correct. 5 questions correct, 6C5, 0.8 to the power 5, 0.2 to the power 1. 6 questions correct, 6C6, 0.8 to the power 6 into 0.2 to the power 0, which is 1. Now you add up all these probabilities. That will be the probability that at least 4 of them will be correct. 4 or 5 or 6 will be correct. So typically, again, 6C4, 6 into 5 into 4 into 3 into 2 into 1. So it actually works out to 6 into 5 into 4 factorial divided by 4 factorial into 2, which actually comes out to 15. So 15 into 0.8 to the power 4 into 0.2 squared plus 65 is 6 into 0.8 to the power 5 into 0.2 plus 66 is 1, 0.8 to the power 6. You can very well simplify this expression, which will give you what is the chance that at least 4 questions will be right. Right? So this is how we simplify the binomial distribution kind of question. So for the principle of that is, I really need to see that there are n independent and identical trials, out of which I want to track x successes. I can easily find out what is the probability of success as well as probability of failure. So out of n trials getting x successes, this is the probability. And couple of more things to be comfortable with. The mean in case of binomial distribution is NP. So here also, if you want, right? So if what is the mean number of questions that would be correct? What would be the average number of questions that would be correct in this case? NP. N is 6, 8 is P is 0.8. So around 4.8 questions will be correct. So somewhere around 5 will definitely, on an average, 5 questions will be correct in this case. That is the mean. The variance is given as NP into 1 minus P, which is 4.8 into 0.2. So almost 0.96. So that is the variance that is present in the data. Square root of variance is the standard deviation for it. So this is what we do with a binomial distribution. Then the next thing is a geometric, which is also on the same lines as binomial, in the sense n independent and identical trials itself. But here we don't know the n. How many trials are being made, we don't know. Here the focus is, I am trying to model how many trials have to be performed before the first success. How many times I have to repeat the experiment, right? How many times I have to repeat the experiment to get the first success. Like if I say getting a 6 on the roll of a dice is a success, right? What is the chance that I will get 6 in 1 trial, 2 trials, 3 trials, right? How many? So for each one I am trying to give a probability. What is the chance that I can achieve it in the first trial itself? I will get success in the first attempt itself. I will get success in the second, third, fourth, fifth, 10th. Let's say it's like this. Probably if I say passing a CT3 exam is, let's say, 30%. Right? It's like what is the number of attempts I have to make before I pass the exam? What is the number of attempts I have to make before I pass the exam? So where I am looking at, what is the chance I can pass it in the first attempt? What is the chance that I can pass it in the second, third, fourth, fifth, sixth, any number of attempts? So number of trials to be performed before you get the first success. So which means we are talking about a waiting time, right? So this is typically a one category of distributions called as the waiting time distributions. We'll see a lot of other distributions which will focus on the waiting time kind of an example, right? So what we are saying is if I am talking of my xth trial or nth trial is a success, then all n-1 trials should be failures, right? So there are n-1 or x-1 failures before the xth trial is a success. Now you can write it in the Bernoulli form, right? So what we are saying, probability of success, there is only one success. You are performing the experiment x times. There are only one success, which is, so that we are writing it as probability of success into probability of failure to the power number of failures. I am having x-1 failures and one success. So this is the probability of getting a success in the xth attempt. Xth trial, the probability of getting a success. So basically, probably we can take that same example. Let's say if I am talking about the, let's say the chance of success in a CT3 exam is 0.3, 30% chance of success. So let's try to model it and see how it comes. Let's say the probability of success in a CT3 exam is 0.3. So the probability of failure is 0.7. Now what is the chance that I will get a success in the first attempt itself? Which means 0 failures are there. Probability of success to the power 1, right, which is as it is, into 1 minus probability of success, which is this, to the power this minus 0, because 0 failures are there if I am clearing it in the first attempt itself. This minus 1. Now you see, so I can say that the chance of succeeding in the first attempt is 30% for this. Now if I look at it across, then the chance of succeeding in the second attempt is 21%, which means there is one failure and then a success. So how did I get it? One failure is p power 1, which is 0.3 power 1 into the failure 0.7 to the power 1, which is what is giving me 0.21. Then we are talking about the third attempt is a success, which means first two attempts are failures. So 0.7 to the power 2, two failures are there. And the third attempt is a success, which is 0.3. So 0.7 into 0.7 into 0.3 will give me 0.147. So there is a 14.7% chance that I will become successful in the third attempt. There is a 10.29% chance that I will become successful in the fourth attempt. Right? Probably this is a kind of a distribution. Now if I try adding up all these, it will generally come out close to 1 itself. The sum of all the probabilities should become 1, because which means even there could be why only 9. Probably I may not make any pass in the 15 attempts also. Right? So then, the chance of passing in the 16th attempt is only 0.1%. Right? So this is the way the binomial, the geometric distribution is typically characterized. If I am talking about the xth success, the first success is coming in the nth attempt or xth attempt, which means x minus 1 failures would definitely be there in that. So the probability of getting success in the xth attempt is what is being modeled through this typical formula. So if we are talking about a question which talks about find the probability of getting the xth success, right, or the first success in the xth attempt, we can model it as the geometric distribution itself. Right? And again, the mean of the distribution is this much, the variance is this much. And because, see, this is a very important rule to use. You don't need to go with this remembering of this rule. Sometimes the question what he says is, what is the chance of getting a success in the 10th attempt, given that he was not successful in the first 6 attempts? Getting my question? What is the chance of getting a success in the 10th attempt, given that he did not get success in the first 6 attempts? Always look at it very simple, because these are independent and identical kind of stuff. It's as good as what is the chance of getting a success in the 4th attempt. So 6 you forget about. The 6 dependency is not there at all. So when he asks the question, this is the one confusing question which he generally asks. What is the chance that he gets success in the 10th attempt, where you already know that he is not successful even up to the 6th attempt? This information is of not much use for us. And simple way that we can model it is, what is the chance that he becomes success in the 4th attempt? Because after 6, there are only 4 more attempts that are required. Right? So you find out, as good as the formula, you apply it, finding out what is the chance of getting success in the 4th attempt itself. Right? This is one important rule we have to remember as far as the geometric distribution is concerned, because they are independent and identically distributed kind of trials. And one more thing which people typically use to model use see, one example where we use geometric distribution is number of attempts to be made to get the first success. Slightly, if I put it differently, number of failures before the first success. Both of them are more or less related. Number of attempts to be made, which is always one less than number of attempts to be made before the first success. Right? If you understand these two English terms, number of attempts to be made to get the first success. If I say 10 attempts to be made to get the first success, then it is nothing but 9 failures before the first success. One lesser than that. Right? So, to find out any of these two requirements, people will use the geometric distribution itself. So, if I want to find out X failures, what is the chance of getting X failures before the first success? Probability of success, probability of success, probability of failure to the power of X failures. Right? And the mean is 1 lesser than the mean of the earlier case. In the earlier case, the mean was 1 by P. Now, because it is 1 lesser than that, because number of failures will always be 1 less than number of attempts for the first success. So, in this case, your mean will become 1 by P minus 1, which is nothing but 1 minus P by P. Whereas variance is still the same as 1 minus P by P square. So, all these formulas are there in your actuarial tables. But the only thing we have to remember is in what kind of question I need to use. Because he will never say this is following a negative this is following a geometric distribution. He will not use those words. He will simply say these are probably n identical trials have been performed. Identical and independent trials are being performed. Right? And the chance of success is something. So what is the probability that he will take 10 attempts to get the first success? So you have to assume that you have to go with the geometric distribution on your own and do the modeling and get your values. Right? Then the next category of distribution is nothing but an extension to the geometric, or probably a generalized version of geometric. Generalized version of geometric, which is called as a negative binomial. Why did I call it as generalized version? The geometric, what are we saying? First success. Number of attempts to make to get the first success. Right? Or number of failures before the first success. Negative binomial says kth success. Not necessarily the first one. Right? Or number of attempts to make to get the fourth success. Or number of failures before the fourth success. Right? Both the things. Number of attempts to be made to get the kth success. If it is first success, then I can directly use geometric. But if I am looking at kth success or number of failures before the kth success, then I am resorting to negative binomial kind of a distribution, which is a slightly generalized form of. So in this case, what should be the thing? So in some x attempts, let's say if xth trial is my kth success. Right? If my xth trial is my kth success, then what should have been the scenario? In x minus 1 trials, I would definitely have k minus 1 successes only. Right? See, my 10th attempt, let's say, is my 4th successful attempt. Which means in 9 attempts, I would have become successful only 3 times. In whatever order, I am not bothered. I want to see the 10th attempt is my 4th successful attempt. So the other way of putting it is, the up to 9 attempts, right? In the first 9 attempts, he has been successful only 3 times. That should be the case. So that's where we are saying, what is the chance of being successful 3 times in the first 9 attempts? So in x minus 1 attempts, being successful k minus 1 times is given by this, and probability of k, there are k successes, right? There are k successes because the 4th success is also there. Getting it? So it's a simple binomial distribution itself. If I try to understand this, I want to find out what is the chance of getting my 10th attempt as the 4th success. So simple thing I am saying is, what is the chance that I am successful 3 times in 9 attempts? In the first 9 attempts. So in the first x minus 1 attempt, what is the chance that I was successful? K minus 1 times. So what is that chance? X. So I can use it as a binomial distribution. In x minus 1 attempts, I am successful k minus 1 times. So using the binomial distribution formula, this is nothing but p power k minus 1 into 1 minus p to the power x minus 1 minus k minus 1, which is x minus k. This is in x minus 1 attempts getting k minus 1 successes. Now the kth one is a success. I mean the next one is a success. So multiply it by p. So that's where this becomes here in the power, it becomes p power k. Because your p power k minus 1, you are multiplying it by p. So it is becoming p power k, 1 minus p power x minus k. So that is where this formula is coming up. So getting x successes or xth attempt to be your kth success, you are using this kind of a formula. But look at it from a business standpoint. See, I want the 10th trial to be my 4th success, right? I am not saying in 10 attempts getting 4 successes. That's not the one. I am saying my 10th trial should be my 4th success, right? Which means it's as good as saying there are 2 points in it. Up to 9 trials, 9 attempts, I would have successful 3 times, right? And the 10th is a success. That is only the thing which says I cleared it in the 10th attempt, right? Otherwise, if I just say getting 4 successes in 10 attempts, then it could also include probably clearing it in the 4th attempt itself. All 4 successes in the first 4 itself. All these are possible. But if I want, no, the 4th clearance happened only in the 10th attempt. Right? Like claims. The 4th claim has been made by the person in the 10th year. I don't want 4 claims in last 10 years. That's a different model for me. I am seeing what is the chance that he will take at least 10 years or he will take 10 years to make 4 claims. Probably the simple way of putting it. So what is the chance that he will take 4 years or 10 years to make 4 claims? So probably in 9 years, he should have made only 3 claims. And in the 10th year, 1 more claim, making it that 4 claims are getting done or getting completed only in the 10th year. Getting it? That's the reason first I looked one part of it which is only for 9 years. X minus 1 C k minus 1 p power k minus 1 1 minus p power x minus 1 minus k minus 1, which is x minus k. This is up to 9 trials. In the 10th trial, definitely it's a success, which is what is the probability of success I am multiplying it with. So overall it is becoming p power k. Getting it? Now, if you simplify it, okay, probability of getting the xth trial, if you try it with x minus 1 trials, right, these two can be linked even through this formula without solving it. See, what is the chance that he is getting successful in the 10th attempt, and what is the chance that he is getting successful in the 9th attempt? If I want to see from the 9th attempt directly, I want to find out what is the chance that he will be successful in the 10th attempt. I can use this recursive kind of a formula, which is nothing but the probability that he will be successful in the 10th attempt is equal to 10 minus 1, which is 9, by 10 minus k, which is 6. K is 4th attempt, 4th success. K is 4 into 1 minus p. 1 minus p for me is whatever. The p is, let's say, if we are talking about a p of 20% or something, then 0.8 into p of x equal to 9. So once I know the probability that he was successful in the 9th attempt, just by doing this additional multiplication of the probability on the 9th attempt, I can find the probability for the 10th attempt. Otherwise, simple thing is use the formula every time. If you are not able to bring out this recursive relationship, no problem at all. You can very well substitute it for x equal to 10, x equal to 9 separately into that formula, into your main formula, x minus 1, c, k minus 1, and get the probability of each of the scenarios. So the mean is, because this is a special case of, this is a generalized case of geometric, kth success. In geometric we said mean is 1 by p. Here it is k by p, because it's a generalized form. Kth success. Geometric was first success. So wherever the mean and the variance are same as the geometric only, instead of 1 we are using k. K into 1 minus p by p squared. In the geometric case it was 1 into y, it was the variance was 1 minus p by p squared. Here it is k into 1 minus p by p squared. So you have to just try to understand what should I use, geometric or negative binomial. Both of actually you can use negative binomial for everything. Geometric is only one special case of negative binomial where we are talking of first success. But this is a general one for any success. For kth success, this negative binomial is typically used. Similarly, the same logic, k failures or x failures before the kth success. Just like the way there also we did, what is the chance of having x failures before the first success? Here also we are talking of x failures before the kth success. So if I am talking about the kth success and x failures, kth success. So k minus 1 I would have already become successful. If we are talking of kth success to come up, for now I would have already got k minus 1 successes and x failures. X failures are there, k minus 1 successes are there. So till now I would have made x plus k minus 1 attempts. I had x failures till now. K minus 1 successes are there because I want to find out now the kth success. So I already have x failures over. K minus 1 successes are already there. So I am trying to find out in this many attempts x failures, the probability of probability of success k, 1 minus probability of failures, which is x. I had x failures, or here I have k minus 1 successes, right? And now the current one should be a success. So which becomes, this will become p power k. So I can even try finding out. These formulas are already there. You need to understand the context. Did he give the question of finding out the number of trials for the kth success or number of failures before the kth success? Number of trials for the kth success is called as a type 1 negative binomial distribution. In the formulas, he gives it as a type 1. I mean, because there are two different applications of negative binomial. One is to model the number of trials for the kth success. Two is number of failures before the kth success. So the number of failures before the kth success, we take them as negative binomial type 2. Number of trials for the for the kth success, we are taking it as negative binomial type 1 kind of a distribution. Then there is another distribution called hypergeometric distribution. Right? There are a couple of them more. We are talking about a hypergeometric kind of a distribution. It's more similar to binomial, but there are some important things here. In binomial, we talked about independent trials. Here we don't talk about independent trials. Here we talk about dependencies. Right? Probably it's like, if you understand this question, it becomes more simple for you. See, in an exam, out of 60 questions, the person has answered only 35 questions correctly. Now, what the examiner is doing is, he is not considering all the 60 questions for the grading purpose. At random, he is pulling out only 5 of them. At random, he is pulling only 5 of them out of that 60. And I want to find out what is the chance that he is getting all 5 correct. What is the chance that he is getting 4 of them correct, 3 of them correct, 2 of them correct, 1 of them correct, none of them correct. So there is a dependency here. Right? We are not talking about out of the 60 questions, what is the chance of or out of, it's not the case like out of 5 questions attempted, right? If the question has been, if he has attempted 5 questions, what is the chance that he is succeeding in 0 of them or 1 of them, 2 of them? Then it becomes binomial. But here my requirement is slightly above that binomial. Though the second part of the question is, if I am taking 5 questions, what is the chance that he is getting 0 of them correct or 1 of them correct or 2 of them correct? That part is a binomial distribution. But there is one more information on the top of that. That out of the 60 questions that are there, he got only 35 correct. Right? So there are 2 ways we can do it. One, we can use what is called as a binomial approximation mechanism, because this is looking more like a binomial distribution. People talk about using a binomial approximation method for that. What people say here is, you take the probability of success from the available information. 35 by 60. That you take it as probability of success. Or for simplicity purpose, let me make this as 36. 36 questions are answered correctly. So 36 by 60. So probably people say you can take your probability of success directly from the original information that you have. The probability of failure is 0.4. Right? And from here, you can use your binomial distribution. Let's say 5 questions attempted, 0 correct, 0 successes. Right? 0 correct, 0.6 power 0 into 0.4 to the power 5. How much is this I am getting? 5C0 is 1, 0.6 power 0 is 1. So all I need is 0.4 to the power 5. Equal to 0.4 to the power 5. So it is saying around 1.024% chance is there that out of the 5 questions that are being picked, none of them is correct. Now if I use it using the hypergeometric method, that is a binomial approximation method, where I made some kind of adjustment. Directly I have looked at the probability of success using the original information that is available to us. Using the original information that is available to us, we have looked at the probability of success and used it into the binomial function. Because the moves are not independent of each other, we'll find the probabilities to be actually different, because binomial distribution assumes that the trials are independent. Whereas in this case what happens, depending on the question that is being picked up, there is a dependency part there. So if I have to do it using hypergeometric, what will I do? There are 60 questions, 36 are correct. So the first question, I have to definitely pick it up as the wrong. The first question, if all 5 should be wrong, the first question should be wrong. What is the chance of first question being wrong? 24 by 60. Out of the 60 questions, 24 are wrong. So the probability that I am picking up a wrong question, the first question, whatever he has attempted is wrong, is being picked, is 24 by 60. Second question also should be wrong. Because I have picked up one question already, I cannot pick it again. So there are only 59 questions now, and 23 of them only are possible to be picked. So I'll write it as 23 by 59. That's the second one. So what is happening is the probabilities of success and failures are actually changing here. That is the reason we cannot use binomial distribution. Now what about the third? 22 by 58. The fourth is 21 by 57. And the fifth is 20 by 56. So these are the probabilities that all the 5 questions are wrong. Now what you can do is you multiply all of them. You multiply all of them, and this is 0.007. The actual probability is 0.007, whereas when you have used a binomial approximation of that, you have got it as 0.010. 1.02% you got here, there you got 0.77%. There will be a difference. So you have to make sure whether the trials are actually independent or not. In that example, the trials are not independent. So that's the reason I cannot use a binomial distribution. And in that case, I have to resort to the hypergeometric, where the solution comes through this kind of a mechanism itself. And the only thing in case of hypergeometric is the means will match with your binomial. The average value will definitely be a match. So here if I am talking about the mean of this in this example 5, because I am making 5 questions are being picked up at random. K is in the original whatever are the successes out of the 6. So there is a point, so this is 3, which you will get it even when you are using the binomial approximation also. The average is 3. So the average is same when you are using a binomial approximation method or the hypergeometric method. But the probabilities of each of them will be different because of the dependencies which you are typically trying to bring them up. So this is one category of distribution we have to be comfortable with. And finally, one more distribution that we need to be comfortable with in the discrete case is the Poisson. Whenever the questions talk about the number of events occurring in a specific interval of time, right? Number of claims within the next 1 year. So the time period is mentioned during a particular period of time, right? So whenever we are talking about modeling the number of events in a particular period of time, we start thinking of using the Poisson distribution. That is one application. The second application is the n is, so in the binomial case, let's say an experiment is performed 1000 times, right? Not 2 times, not 10 times, not 20 times, but very large number of times, and the probability of success is very, very small, right? Probably 0.001. If the probability of success is very, very small, then also I can use Poisson, which means Poisson is nothing but an approximation of the binomial distribution. The linkage between binomial and Poisson is like this. The number of trials should be very large and the probability of success should be very small, such that when I multiply the probability number of trials into probability of success, NP, which is nothing but the mean of the binomial distribution, this should be more or less constant. If NP becomes more or less constant, I can use it as a Poisson distribution. So I will not consider N and P separately here. I will take their multiplication, which is constant, and I will have only one parameter called lambda. So using that, I can very well model the probability of getting X successes using this kind of a formula. Lambda power X into e power minus lambda by X factorial. If I take a numerical, it becomes easier. Look at this one. The probably look at the first one, then we'll go to the second. If the rate at which the goals are scored in a game of football is on an average 3 every match, right? So the constant is 3. So the lambda is equal to 3 here. 3 per match. 3 per match. What is the chance that more than 5 goals are scored in a match? 5 means it could, or probably will say that 5 goals are, let's not use more than. What is the chance that 5 goals are scored in a match? So all I need is, I need P of X equal to 5. More than means I need to find P of X equal to 6, X equal to 7 and all those things. But at higher values, it becomes almost minute. The probabilities become much, much lesser. Okay, so P of X equal to 5, if I have to find out, it is nothing but lambda power 5. Lambda is 3 in our example. 3 power 5 into e power minus 3 by 5 factorial. How much is this working out to? 3 power 5 into e power minus 3 divided by 5 factorial. Comes out to 0.10. So there is a 10% chance. So probably you can model it. This is a very real world problem, right? If typically there are 3 goals that are scored in any particular match on an average. On an average, we are seeing that around 3 goals are being scored, right? Then what we are trying to say is, what is the chance that 5 goals are scored? Because on an average it is 3. I want to find out what is the chance that not even a single goal is scored in a match. What is the chance of scoring 1 goal in a match, right? So that I can model as a Poisson distribution itself, where the average is constant. The probability of success is probably, if I am looking at the number of minutes of the match, 500 minutes. or probably seconds, 5,000 seconds. Goal is nothing but it's a spontaneous thing. So probably in 3 seconds you had a success, which is nothing but 3 goals. So the probability of success is very, very less. Number of trials is very, very large. In those cases, I am taking the multiplication of that, treating it as a constant and using it for my modeling purpose. The same thing, look at the next question. The number of home insurance claims a company receives in a month is taken as a Poisson distribution with a mean of 2. In a month, it is taken as 2. What is the probability that the company receives exactly 30 claims in a year? Either I can make it as 24 in a year, or I can take it as 2.5 in a month. One of them I can translate it to. So simple thing, probably instead of doing big calculations, I'll try to take the other way itself, 2.5 claims in a month. So I'll make it as probability of x equal to 2.5. Lambda power 2.5 e power minus lambda divided by 2.5 factorial. Whatever is the value that comes out, we can very well take that formula. Right? So this is how we can use the Poisson distribution also as a part of our modeling. So we are typically looking at all number of only. If you look at the commonality in all these distributions, number of successes in n attempts, binomial. Number of attempts for the first success, geometric. Number of failures before the first success, another geometric. Number of attempts for the kth success, negative binomial. Number of failures before the kth success, again type 2 negative binomial. From a number of successes from a non-identical and independent distribution, hypergeometric. And number of successes where n is very large or within a specific interval of time, Poisson. So typically at the end we are talking about modeling the number of something itself in various circumstances which are leading to various distributions for us. The same way, so all you have to do in this is the formulas you don't need to mug up, but you need to understand the context in which all these things have to be used. Right? Just by looking at the numerical question, you should be able to make out that I should use this kind of a distribution in this context, and immediately you know the mean variance. You can visit the formulas, check out for the mean variance of each of them, and you can try to find out your calculation. So this comfort you should definitely get if you have to attempt either the other subjects based on CT3 or even the next chapters also. Right?